The exercise for this week is going to be calculating the strain within a contractional fault system. So the exercise, we're going to be calculating what's called bulk strain. So this is the strain basically within the entire system. So we're not just going to look at one layer or one lithology. We're going to take an entire system and look at it together. So this figure is from the paper that's mentioned in the introduction above. There is a line drawing of 5 stages of a single experiment. The thicker layers are made of stiffer material than the thinner layers. And if you think about the deformation, well, we haven't seen the one in Wisconsin, so we won't talk about that. But this is the image that these figures are referring to. So up here, the very, very top layer, that's our thick layer, thin layer, thick layer, thin layer, thick layer. All right, so exercise 1. The first part, you're going to form in your regular groups, and you're going to choose or create a unit of measure. Right, I'm just going to use my protractor with my centimeter scale down here. But when we're measuring bulk strain, it is unitless, non-dimensional, so you guys can use whatever you want, just as long as you define it. So have each person in your group calculate the bulk shortening for the different stages of deformation, using the top image as the reference point for the undeformed state. In order to calculate this, you estimate the average length for both the deformed and the undeformed state. Compare the 4 answers between everybody in your group. Do they make sense? That is, do your estimates form a natural progression from a least deformed to a most deformed? So right here, undeformed state, you're going to measure it, and we want the entire length, right? So it's maybe about 10, maybe about 14 centimeters for our undeformed state. And then your natural progression, how short do each one of these get? So undeformed to deformed, calculate the shortening, right? By the undeformed, by the deformed, and see what you get. All right, the next one, you're going to calculate the bulk thickening for each of the stages of deformation in the same way. Right, so instead of overall thickness this way, you're going to do, or overall shortening this way, you're going to do thickness of each layer. Right, so we've got 3 millimeters here, 3 millimeters there, but these guys are thickening up, 4 millimeters, and so on. So again, calculate the difference in thicknesses between those two. Compare your answers. I want you guys to write this up. So, you know, here's the questions, but on a separate piece of paper, or you can type it up. Write your answers for each. Question 4, has there been any change in cross-sectional area during deformation? If so, approximately how much? Right, so we are looking at a cross-section. This is a side view. So you take the earth, cut it in half, and you're going to be looking at this. So is there any change in the area? So that is going to be your height times your width. That's how you calculate area. And then calculating, is the strain 2-dimensional or 3-dimensional or 1-dimensional? Right, we're trying to think 3-dimensionally. Think about a contractional system, right, where you have 2 things that are coming together. Things are getting deformed, but this is cross-section. We got to think about what's happening on the top. So think about those dimensions and see what makes sense. Let me know what you think. This one is going to be for you guys, right? Describe the bulk deformation process to each other using gestures, right? Hand gestures, peace sign, thumbs up. Those are gestures, right? So you might need to work together. Obviously, you're going to have shortening in one direction, thickening in another direction, so you only have 2 hands. Be creative, have fun with it, but I do want you to do this part. And question 7, we want to calculate the overall thickening in one of the thick layers from the beginning to the end of the whole deformation. So this is, you don't have to calculate for each stage, you just calculate it from one to the last. So these two. And that's due to a process called layer parallel shortening. I will talk about this on our field trip. So it's important that you guys at least do this process so that when I talk about layer parallel shortening, you can understand what I'm saying. All right, and then exercise 2, we're going to be talking about strain accommodation. So what specific kinds of structures accommodate the shortening and thickening you observe? Can you guesstimate, right, which type of structures accommodate the most strain? And don't forget that layer parallel shortening accommodates some of the shortening. In this case, maybe look it up to answer this question. If you can't answer that right away, that's okay. I won't count that against you, but try to look it up, see if you guys can find a definition, so when we talk about it on the field trip, you will get an idea. But notice, right, there's definitely a difference between the behavior of the thin layer and the thick layer right here. So that will help you to figure this out. So that is the assignment for this week that I'm gone. Guys, hope you have fun. I have loaded this on the Canvas page, so you should have access to it printed out. Yeah, and have fun.